These are TMUA questions about finding the counterexample. So for instance, which one of these values is a counterexample to stuff that's going on here? Now the very first thing that we need to get over is they always or almost always give you if-then statements when doing this. And what's really important is that you read the if statement. This is the first thing we'll do every single time. If n is a prime number. Now the first few primes are these. If n, now n is the un bit, right? Where is it? There, un. So we want a prime number as this little subscript here. So we don't care about this, we don't care about this, we don't care about this. It says if n is a prime. Imagine you're, at school or college and you're in some kind of assembly and the teacher at the front says, if you haven't completed your UCAS thing, blah, 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 you stop listening if you have, right? The statement, if you haven't completed your UCAS thing, doesn't apply to you if you have. This statement here, whatever it goes on to say, does not apply to the numbers who do not have primes down here, because it says if n is a prime. So we get rid of all those. Now we read the rest of it. Then un is a multiple of 3, or un is a multiple of 5. Next really important thing is that or in TMUA means and or, which is a bit confusing and really tripped me up the first time I ever saw this. But when they say or, it can be both 3 and 5. It doesn't have to be one or the other. It can be both, which is really weird. I don't know why they do it like that. But anyway, u2 is a multiple of 3, right? It's 3 times 7. So that's not a counterexample. u3 is 3 times 10. It's also 5 times 6, but we're allowed to be both, according to TMUA's weird rules. So that's not a counterexample. 44 is neither a multiple of 3 or 5, but n is a prime number, and so therefore that's the first counterexample, and so n is 5 is the first one here. Next thing, exactly the same. Every positive integer n that is greater than 6. So we're going to ignore questions where n is not greater than 6. So I haven't read the rest of the statement yet, but I'm going to get rid of this one because it doesn't do the first bit. Can be written as the sum of two non-prime integers that are greater than 1. So let's just write out all the things that 7 can be the sum of. This, and this. Any of them two non-prime integers greater than 1. Well, these are both non-prime, but one of them is 1, so that doesn't count. Both of those are prime, so that's not okay, and only one of these is prime. So 7 cannot be written as two non-prime integers greater than 1, so 7 is a counterexample. It's bigger than 6 and can't be written in the way they want, so 7 is a counterexample. What about 9? Well, again, just write them all out. These are both non-prime, but one is 1 again, so it's the same situation as here. Both of these are prime, so no, one of those is prime, and so is one of those. So 9 is in the same boat. It's bigger than 6 and cannot be written as the sum of two non-prime integers greater than 1. So both of those are counterexamples. Next one, if a is a factor of bc. So let's just check bc out for all of these. That's 200, 16, and 84. Is a factor of those? Yes, every time, fine. So we can't get rid of any of them based on this, but that's okay. Then a is a factor of b, or, and again that means and or, so it's allowed to be both. Then a is a factor of b, or, and c. Well, a is a factor of both those things, so that's not a counterexample. 8 is not a factor of 4 or a factor of 4, so that is a counterexample. 6 is not a factor of 7, but it is of 12, so 2 is the only one that doesn't have either. A is not a factor of either of the other two, so 2 is the counterexample. Okay, so another one. Again, reading the first statement really carefully. If f dashed of x is greater than 0 for all real x. So let's find f dashed of x every time. So here it's just 2x. That's clearly not bigger than 0 for all real x. Just put x as minus 1 in. So that cannot be the counterexample. Again, I haven't read this yet, and I don't intend to until I deal with this every time. So okay, that's not the counterexample because it doesn't obey this. This clearly not because it's the same thing, so no. This actually is greater than 0 for all real x because this of course is a square. Add 1, so that actually does the first thing. Then f of x is greater than 0 for all x. Well, if you just put in minus 10 into this, very clearly you're going to be less than 0. So this is the counterexample. And it actually only asks for 1, so you can stop working there. This is the counterexample, because this is bigger than 0 here. This is bigger than 0, but this isn't. Cubics are always positive somewhere and negative somewhere else, which you could have just known to save yourself working this out. But that's the counterexample. For completion's sake, you might want to differentiate this and show that, okay, well, this clearly doesn't obey the first law. This does, right? If you don't know how to differentiate exponentials yet, you just keep the exponential like it is, and then just write log 2 next to it. Now this is positive for all real x, and also the exponential itself is positive for all real x. And so it's not a counterexample because it obeys both of these things. This is the counterexample. We could have stopped working as soon as we found it. Cool. Another one then. So if f of x is an integer for every x, we know what we're going to do. We're going to go straight down to here without reading the rest of it and check which ones are integers for every integer x, or to try and find a counterexample that makes it not. So clearly I can see that f of 0 is a quarter. So this function is not an integer for every integer x. So goodbye. Also, if I put 1 into here, I'm going to get 3 over 2 quite clearly. So goodbye. I'm down to 2 functions here, which is a good start. I can't really find a counterexample to this, and in fact, I can quite quickly, hopefully, when you're talking about integers, a good thing to always think of is odds and evens. So this function here is either even plus even plus even plus even if x is even, or odd plus odd plus odd plus odd if x is odd, because of course when you raise odds to powers, you just make more odd numbers. But of course, odd plus odd is even, so it's 2 evens added together divided by 2, which is of course even. And of course this is going to be even as well. So this is an integer for every integer x. So okay, it does actually obey the first bit. Let's look at the second bit. F dashed of x. Let's differentiate it. We'll get this. I hope I've differentiated that correctly. Now, is that an integer for every integer x? Well, very clearly, I can see that if I put 0 into this, I'm just going to end up with a half. So that's not an integer for every integer x, because there's a counterexample. So that's the counterexample to the whole thing, because it does this, but it doesn't do this. So that's the counterexample. Again, I can stop working here, or I could maybe look at D if I wanted to, just for completion's sake. Again, in the real paper, stop working there. You don't want to waste your time on this. But for completion's sake, looking at D here, if I factorize out the x squared, I then notice this factorizes. And I can argue this is an integer for every integer x, because if x is even, again, thinking about odds and evens, if x is even, then it has a factor of 2 in it, by definition of an even number. So when I square that, I'm going to have 2 factors of 2, which will cancel with this 4, and I'll get an integer. If x is odd, then x plus 1 is even, therefore having a factor of 2. When I square it, it will have 2 factors of 2, cancel with the 4, and this will be an integer as well. So this is definitely fine for the first bit. And then I differentiate it. So this is it differentiated. This looks like it won't be an integer for every integer x at first glance. Factorize out the x, and now factorize out a half, which looks a bit weird, but bear with me, because now this thing can factorize to make this. And again, this doesn't look like it will be an integer for every integer x, thereby being a second counterexample, which can't be the case. But think about odds and evens again. You've got an x and an x plus 1 here. If x is even, then this half will just make an integer with it. And if x is odd, then this half, then x plus 1 is even, and then it will multiply out this half, and you'll just end up with an integer again. So that one is always an integer for both cases, thereby not being a counterexample, and C was the answer all along. I think we're just going to do 1 or 2 more, hopefully. Again, if f of x squared is less than 1 for all of this, so the first thing we're going to do is deal with that. So I could square all of these functions out and find some expressions, but I can't be bothered. I'm just going to put in some values and then square it. So, for example, if I do f of 1, that's clearly 3 over 2. And if I square it, that's clearly bigger than 1. And I'm allowed to put in 1, right, from here. So that's not the counterexample, because it doesn't obey the first bit. Likewise here, I can't put f of 1 in, because that will make a half squared, which is less than 1. But I can put in minus 1, because that will make minus 3 over 2, which when I square it is still greater than 1. So that can't be it either. This one I can find a very easy counterexample for. Just put in 1, you get 2, which is, okay, so that goes away. This one I can't find one easy for. This one is very easy, right? 1 squared plus 1 to the 4 is 2 again, so that one breaks it. These two, it's harder to find any counterexamples for this cases. You can check each extreme, minus 1 and 1, and they both still work. So okay, we move into the next stage, but notice how the question only asks for one counterexample. So all I need to do is check one of these two, and if it's the counterexample, then I'll tick it. If it's not, then the other one must be. So that's quite nice of them. So I'm just going to check this one here, and regardless of whether or not it works, I'll only need to check one of them. So let's do this one here. So let's square the function out, which makes this, and then let's integrate it like it says. And I want this, well, I don't really care what it turns out to be, because I'll just select the other one if it doesn't quite work. What you can notice about this if you want to, if you haven't seen this before, that's fine, because I'm sure we can all integrate this anyway. But this is an even function because it just has even powers of x. And even functions, when you integrate them between a symmetrical range like this, are just double the range between, in this case, 0 and 1. So if you're going from -5 to 5, it will just be double from 0 to 5. And that's easy, but this makes it a bit easier because when I integrate this, substituting in 0 is really, really easy, so it makes it a bit easier. And I deal with all the fractions and I eventually get this. Okay, so I'm done with that. So this is that number, and then so that's this bit, and then I need to deal with this bit. But again, this is an odd function because it's x to the 1, x to the 3, odd numbers, so it's an odd function. And odd functions don't behave like this. Odd functions behave in that if you're integrating them over a symmetrical range, they just make 0. And so this value, which is this, is actually bigger than this, and therefore this is a counterexample because it does this but doesn't do that. And therefore this one must have been the one that did work, but this is the counterexample. If you're not sure what I'm doing with these odd and even functions, search some videos up on them. They're really interesting. Otherwise, you could have just done the integrating properly. I just couldn't be bothered. That is the every question I was planning to do. Good. I couldn't remember how many I was doing. But the key thing here is if you're reading statements like this, you've got to read the first bit first carefully and disregard anything that doesn't obey it. That was the point I was trying to get across. Once you've narrowed down the ones that do, then you deal with the second bit. That's the way that we're going to do it every single time. Thank you for watching.